Let's revisit orbital forcing. We have used this word, we have seen a bit of it before. We mentioned changes in obliquity, ellipticity, and precession. Let's look at it more in the context of the ice ages. We will see more and more of past variability a little bit later on to understand one of the most important feedbacks in the system. So the name associated here is Milutin Milankovitch. There is another name, James Kroll, that's preceded this, but nonetheless, these ice age cycles are called Milankovitch cycles because he was the first one to mathematically put down the calculations of the eccentricity of the Earth's orbit, the obliquity, and precession. So right now you can sit down and calculate when the next orbital forcing change is going to come about in terms of precession or ellipticity or obliquity and so on, right? So we have seen this already. The circularity or the ellipticity of the orbit changes over 19 to 26,000 year time scale, so more like 23,000 years is the average period of that forcing. Obliquity changes from 22 to 24 and a half. That changes on 41,000 year time scale. We have already mentioned obliquity forcing. And there is precession, which actually includes two things. One is the precession of the axis, so it's like a top. When it slows down, it begins to wobble. So Earth, as a rotating planet going around the sun, wobbles. And then there is another one called apsidal precession, or the precession of the equinoxes. So here is the precession of the axis, which points to different north stars. So you have Vega and Alpha Draconis and Polaris and so on. That happens on the 19 to 26,000 year time scales because of the gravitational pull of the other planets in the solar system, like Venus, Jupiter, Saturn, and so on. Earth's orbit itself gets pulled around, so you can see the animation here, which means the time at which equinoxes and solstices happen as a distance from the sun would change unless you continuously changed the calendar to match the apsidal precession of the orbit itself, right? So obviously when ellipticity changes, the amount of radiation coming in itself would change because the distance from the sun is changing. But as we've said before, the ellipticity is only about 0.02, so it's a very, very tiny amount of change in energy. But it can combine with the precession to create a beat at 100,000 years that we mentioned in terms of the ice ages in the last 2 million years. We'll come back to that a little bit later on. Okay, so that's the orbital forcing, and you will find signatures of climate change at 100,000 years, at 41,000 years, and at the precession cycle. For example, Indian monsoon has a very strong precessional beat in it. Okay, so the greening of Sahara 9,000 years ago to 6,000 years ago, when the civilizations expanded over much of Sahara and back towards the Nile, was a precession beat. There are precession beats in El Nino as well, and so on and so forth. So these are changes in the radiation, or is the changes in the seasonality. So when you change the obliquity, you are not changing the amount of energy being received, but you are changing the hemispheric contrast, because if the obliquity increases, one hemisphere will be pointing more towards the sun and the other one, opposite hemisphere, will be pointing more away from the sun. So the summer hemisphere will receive stronger radiation, and the southern hemisphere will receive lesser in the specific summer season. So the seasonal contrasts will change, and these can lead to other feedbacks that we looked at as some examples. Those feedbacks then amplify the seemingly tiny radiation forces that are associated with these orbital changes. So again, it comes back to feedback. It's not always the amount of energy distribution or amount of energy being received, but it is what kind of feedbacks get kicked in the system that can amplify the initial perturbation. Okay, so if you increase the radiation at 65 degrees north, let's say, that's going to start melting the glacier. That's going to reduce the albedo, further increase the trapping of the solar radiation, further warm the temperatures, increase the glacier melt, and so on, and you can have a positive feedback and melt the glacier away. And the other way, if you reduce radiation at 65 north, why 65 north? Because that's where the summer radiation can determine the amount of melt or buildup of the glaciers and snowfall accumulation through the summer months and so on. Okay, it's these feedbacks to small perturbations that can amplify the perturbation that we are interested in. Again, always trying to see where we are headed into the future with all the perturbations we are making.